Hi everyone. Today we're going to continue our discussion on electrochemistry. So last time we talked more conceptually about electrochemistry, and today we're going to see how we can calculate the potential for a cell. We'll also do some practice problems so we can see how we can apply some of these concepts that we've learned. And first, we're going to start with something called the standard reduction potential. So unfortunately, we cannot measure the absolute tendency of a half reaction. We can only measure it relative to another half reaction. So this would be that E value for a half reaction. So scientists selected a standard half reaction, which is the reduction of hydrogen ions to hydrogen. So down below we'll write that equation. Let's see, so it might start out as aqueous, and then we add 2 electrons, and we end up with hydrogen gas. All right, so down below we can see what's called a standard hydrogen electrode, and we abbreviate that as SHE. And because we're turning an aqueous ion into a gas, we need to use a platinum electrode, or our inert electrode. Because unfortunately we can't just use solid hydrogen. That doesn't really exist at room temperature. So this particular half reaction has a potential difference of 0 volts, or we assign it a potential difference of 0 volts. So we would write that E is equal to 0 volts. So now any other half reaction that we look at has that potential value, and that potential value is going to be either positive or negative, and it's relative to this standard hydrogen electrode. So this figure's a little blurry, I apologize, but in your textbook there is a table 19.1, and this table contains those E values, so those potential values for different half reactions. Now, kind of towards the middle of the table is the standard hydrogen electrode. So I cut this table in half, and you'll notice that above that standard hydrogen electrode, all of the E values are positive. So each of these half reactions have a positive E value. Now you'll also notice that as we go further up the table, we have stronger oxidizing agents. So is an oxidizing agent oxidized or reduced? Reduced. Remember, it's opposite. So if you have an oxidizing agent, it's able to be reduced. So as we go up this table, or as those E values become more positive, that means that that half reaction is going to be reduced more so than any half reaction below it. So for example, let's compare, let's compare chlorine and its reduction reaction to silver. All right, so chlorine is being reduced, so it's gaining 2 electrons to become 2 chloride ions, and it has a value, or its a potential value here, is 1.36 volts. And then let's look at silver. So silver is gaining 1 electron to become a silver neutral, or sorry, silver ions are gaining electrons to become a neutral silver atom. And its electron or potential, I'm tongue-tied today. Its potential value is 0.8 volts. So the potential value for chlorine is a lot higher than that of silver, or it's more positive than that of silver. So chlorine is more likely to be reduced. All right, so now let's look at the other half of the table. So again, we have our standard hydrogen electrode, SHE, and below that reaction, or half reaction, you'll notice that all of the E values are negative, and they're getting more negative as we go down the table. So as we go down the table, these half reactions are showing stronger and stronger reducing agents. So if something is a good reducing agent, is it oxidized or reduced? It's oxidized. So as we go down the table, these different molecules or ions are better oxidized, so they lose electrons more easily. So let's compare a couple of these. Let's compare nickel to aluminum. At least I think that's aluminum. It's a little blurry. All right, so nickel has a potential value of negative 0.23, and aluminum has a potential value of negative 1.66 volts. So aluminum, because it has a more negative potential value, is more likely to be oxidized than nickel. So this table can help us determine in which direction electrons will travel if we put two half reactions together. And we could also combine a half reaction from the top part of the table with a half reaction from the bottom part of the table. And using these potential values, we can determine, okay, are electrons going to travel from, let's say, nickel to iron or from iron to nickel? What will be spontaneous? So let's talk a little bit more about how to figure that out. All right, so just to summarize, higher on the table of standard reduction potentials, so if something is higher up on the table, it has a stronger tendency to be reduced. So higher on the table, stronger tendency for the reactant to be reduced. So we can also just summarize higher up on the table, more likely to be reduced. And then if something is lower on the table, then it has a stronger tendency to be oxidized. Okay. All right, so any reduction reaction in table 19.1 is spontaneous when paired with the reverse of any of the reactions listed below it on the table. So let's actually go back to the table. So you'll notice that everything is gaining electrons. So that's one key part that we didn't really go over. So if we go to the first half of the table, you'll notice that everything is gaining electrons. So they're all in the reactant side. So as we continue down, and then it's the same for the second half of the table as well. So electrons are always in the reactants. So really we're looking at reduction of everything here. So, and then you'll notice on this slide, it said that the higher on the table of standard reduction potentials, the stronger tendency for the reactant to be reduced or gain electrons. And then down below, it says the lower on the table, the stronger tendency for the product to be oxidized. So that's key. So the product will lose electrons. So we're actually going to consider the reverse reaction. So in this example, we have two half reactions where copper is gaining electrons and zinc is gaining electrons. So two ions are becoming neutral atoms here. Now the potential value for copper's reduction is positive 0.34 volts. And the potential for the reduction of zinc is negative 0.76 volts. So how do we figure out what's spontaneous and what's not spontaneous? Well, copper's half reaction is more positive. And remember, if we go back, if something is more positive, it's more likely to be reduced. And if something is more negative, then it's more likely to be oxidized. Okay. So that means we need to flip this second reaction. So this will actually be zinc losing electrons to become an ion. All right. Now, unlike previous practice problems we've done with things like enthalpy and entropy, we don't change the potential of the half reaction. So even though we flipped this half reaction, we're not going to change the sign of the potential value. So it will still be negative 0.76. So that's a really key point. All right, so down below, if we combine our two half reactions, so this one, which is being reduced, and this one, which is being oxidized, we'll end up with our spontaneous reaction, where zinc is reacting with copper 2 plus to produce zinc 2 plus and neutral copper. And then below that, we have the reverse, which is non-spontaneous. So if we try to react pure copper with zinc 2 plus, it's not really going to occur. Okay, so again, we can predict the direction of electron flow by looking at how positive or how negative the potential values are for half reactions. Okay, so again, a half reaction with a strong tendency to occur has a large positive half cell potential. All right, so when two half cells are connected, the electrons will flow so that the half reaction with the stronger tendency will occur. So again, looking at our zinc and copper reactions here. So if zinc is oxidized, that's spontaneous. It has a negative value, so it will spontaneously be oxidized. But if copper is oxidized, it will not be spontaneous. So that's a non-spontaneous process. And that's because it has a positive value for its potential. So again, the more positive the more likely something is to be reduced. The more negative, the more likely something is to be oxidized. So a couple different ways to think about it. All right, so here we're showing how you can measure the half cell potential of a half reaction using that standard hydrogen electrode. So what we would do is we would set up an electrochemical cell like we saw previously. And on the left-hand side, we have zinc as our example, and it's being oxidized, which we said was a spontaneous process. So zinc is going to lose 2 electrons, and then the hydrogen electrode, that's going to be reduced. So any hydrogen ions in solution are going to gain electrons and then produce hydrogen gas. So up above we have our zinc electrode, which is the anode. Remember, oxidation goes with anode, and I just remember it because they both have vowels in the front. Whereas reduction goes with the cathode. So we also have wires that are hooked up to a voltmeter, and electrons are flowing from left to right. And that voltmeter is going to measure the voltage that's occurring due to this transfer of electrons or flow of electrons. So we end up with a value of 0.76, which is the voltage that's associated with zinc and its half reaction. Oh, apparently I need to update my carrier settings again. Not now. So if we go back, remember the value is actually negative because it is spontaneously oxidized. Okay, so this is where those values come from. Also, one thing to point out too is off to the right, we are using an inert electrode, which is the platinum electrode. And again, that's because we can't have like a solid hydrogen metal, or because hydrogen is not a metal. So what ends up happening is electrons travel through this wire, and there's a wire running through that gas tube on the side there, where there's hydrogen gas. And electrons are going to then enter solution and combine with 2 hydrogen ions to produce a hydrogen molecule. And then the gases will just bubble up out of solution. Okay. So again, just a summary, because a lot of this is new information and we really haven't talked about this sort of topic before. So the standard hydrogen electrode reduction potential is defined to be exactly 0. So again, that was the reaction where hydrogen ions were combining with electrons to produce hydrogen gas. And then standard reduction potentials compare the tendency for a particular reduction half reaction to occur relative to the reduction of hydrogen ions to hydrogen gas. So again, if we look back at our table, anything above our standard hydrogen electrode potential will be positive, and so it's more likely to be reduced spontaneously, and anything below that standard hydrogen electrode potential is negative because it's less likely to be reduced but more likely to be oxidized. Okay, so let's go back. All right. So half reactions with a stronger tendency toward reduction then the standard hydrogen electrode have a positive value, and half reactions with a stronger tendency toward oxidation than the standard hydrogen electrode have a negative value. And of course, during quizzes and exams, you can consult that table. I'll try to include it somewhere so that you can easily access it, and hopefully it will be less blurry. All right, so now let's actually calculate the potential for a cell. So to calculate E cell for a reaction, we're going to set that equal to the potential for the reduction half reaction minus the potential for the oxidation reaction. Now, the other way to think of this is, remember, reduction is on the cathode side of our electrochemical cell, and oxidation is on the anode side. So we could also write this as the potential of the cathode minus the potential of the anode. So whichever one is easier for you to remember is totally fine. I tend to use this one down below. So I try to kind of figure out what's being oxidized, what's being reduced, and whatever's being reduced is the cathode, whatever's being oxidized is the anode. And then I just remember that last equation. However, I'll probably give you that equation on quizzes and exams because it'll just be easier. All right, so when we're adding those E values for the half cells, if you need to multiply the half reactions in order to balance them, you do not change those potential values. So this is not like enthalpy or entropy or Gibbs free energy, where let's say we double a reaction in order to balance it with another reaction. We would then double the enthalpy value or the entropy value. But here, we don't touch the E values. They just stay the same no matter what. So do not change those E values. Okay, so let's practice calculating E cell for a reaction. So this is in your textbook, but if you want to see how I solve it, you can stick around or you can just read your textbook, whatever you prefer. So let's use tabulated standard electrode potentials from our table to calculate the standard cell potential for the following reaction. And this is at standard conditions, which is what we measure all of our potentials at. So we have aluminum reacting with nitrate ions and hydrogen ions, and that's producing aluminum ions and nitrogen monoxide and water. All right, so the first thing we should always do is assign oxidation numbers and figure out what is being oxidized and what is being reduced. So aluminum, if it's a pure element, will have an oxidation number of 0. And then for nitrate, oxygen always has a value of -2 in a compound. And there are 3 oxygens, so we have a total of -6 coming from those oxygens. Now remember, we want everything in a polyatomic ion to add up to the charge on the polyatomic ion. So we have nitrogen plus -6 coming from those 3 oxygens, and we want both of those to add up to -1. So nitrogen will be +5 for its oxidation number. Okay, and then we have hydrogen ions. So the oxidation number is the same as the charge. And then in the products, we have an aluminum ion. So again, its oxidation number is the same as the charge. And then for nitrogen monoxide, this is a neutral molecule. And remember that oxygen always has a value of -2 if it's in a compound or a molecule. But remember, if oxygen is just by itself as a diatomic molecule, its oxidation number is 0. So just remember that. All right, so nitrogen in this molecule has to balance the oxidation number of oxygen so that they add up to 0. So nitrogen's oxidation number is just +2. And then in water, hydrogen again has a value of +1 because it's in a molecule, and oxygen has a value of -2. Oh, didn't mean to do that. All right, so I'm just going to erase some of these little scribbles down here to make some room. All right, so let's figure out what is oxidized and what is reduced. So on the left-hand side, we have aluminum with an oxidation number of 0. And then in the products, it has an oxidation number of +3. So is aluminum losing or gaining electrons? It's losing electrons. So is it oxidized or reduced? It's oxidized. Okay, so let's write down our oxidation half reaction. Okay, so it's going to become aluminum 3+. And how many electrons is aluminum losing in this process? 3. Okay. All right, so now let's figure out what is being reduced. So if we look at our other options, we have nitrogen, oxygen, and hydrogen. So hydrogen looks like it's always +1 on the left and the right. Oxygen is always -2 on the left and the right, so neither of those atoms are changing. But nitrogen is going from +5 to +2 in oxidation number. So is nitrogen losing or gaining electrons? So its oxidation number is becoming less positive. So it's gaining electrons. So is it oxidized or reduced? It's reduced. Okay, so let's write out that half reaction. Okay, so NO3. And then I'm still going to keep those hydrogens in this half reaction. Because those hydrogens eventually combine with some of the oxygens from nitrate to form water. So that is part of this half reaction here. And then I'm going to leave a little space for the number of electrons because we still need to figure out how many electrons are gained. And then we end up with NO plus 2H2O. Okay, and then I'm going to put the states in. All right, so now let's figure out how many electrons are gained during this process. All right, so we have a -1 charge from nitrate, and then we have 4 positive charges from those 4 hydrogen ions, and then we have some amount of electrons, and then on the right-hand side we have 2 neutral molecules, so everything should add up to 0. On the left-hand side. Okay, so we end up with +3 plus the number of electrons, which is equal to 0. So the number of electrons, we've got 3. And I keep the negative charge in there just because, but if you have a different way to solve for this, that's totally fine. This is just the way I do it. All right, so that means we have 3 electrons that are gained in this process. And then I'm just going to erase my math down here. Okay, so we've got our 2 half reactions. So now let's look up the electrode or the potentials for these half reactions. So if you want to consult your table and pause the video, you can. So aluminum has a potential equal to negative 1.66 volts. And our other half reaction, where nitrate reacts with 4 hydrogen ions, that has a potential of positive 0.96 volts. Okay, so now we can use our equation where the standard cell potential is equal to the potential of the cathode minus the potential for the anode. Okay, so let's go back and figure out which half reaction would be the cathode and which one would be the anode. Okay, so we said that aluminum is being oxidized. So is that the cathode or the anode? That's the anode. Remember, the two vowels go together. And what about our nitrate and hydrogen ion half reaction? That's undergoing reduction. So is that the anode or the cathode? The cathode. Okay, so now we can just plug in our two values for anode and cathode. All right, so cathode goes first. That would be 0.96 volts. And then we're going to subtract negative 1.66 volts. So we're actually adding them together. So that will give us 2.62 volts. So, extra question, is this a spontaneous reaction or a non-spontaneous reaction? So E cell is positive, so that means it's spontaneous. All right. Okay, so let's do another example. Now, in this example, we're not actually going to calculate the cell potential, but we're going to predict whether each of the redox reactions is spontaneous. If the reaction is spontaneous, as written, we're going to sketch out the electrochemical cell. If the reaction is not spontaneous, as written, then we're going to rewrite the equation so that it is spontaneous, and we'll sketch the electrochemical cell again. So in our sketches, we need to make sure to label the anode, which should be drawn on the left, so that's oxidation, and then the cathode, which will be on the right, and that is reduction. And then we want to show the direction of electron flow. Okay, so let's start by figuring out A. Okay, so we've got iron reacting with magnesium ions to produce iron 2 plus and then magnesium. All right, so let's assign oxidation numbers. So iron initially is just pure iron. It doesn't have a charge, so its oxidation number would be 0. Magnesium is an ion, so its oxidation number matches the charge. And then in the products, we have iron as an ion, so its oxidation number matches the charge. And then we have pure magnesium, so its oxidation number is 0. Okay, so iron changes from 0 to +2. So is it losing electrons or gaining electrons? It's losing electrons. So is it oxidized or reduced? It's oxidized. And then what about magnesium? So magnesium goes from +2 to 0. So is it losing electrons or gaining electrons? Gaining electrons. It's becoming less positive. So then is it oxidized or reduced? It's reduced. Okay, so then we need to figure out, is this a spontaneous process or a non-spontaneous process? All right, so let's look up these half reactions and their potential values. So if you want to pause the video and double check that. So for iron, let's see, the value is negative 0.45 volts. And for magnesium, the potential is, oh, sorry, I shouldn't be writing cell in there, just E. So for magnesium, the value is negative 2.37 volts. Okay, so both of these are negative values. However, magnesium is more negative. So if that half reaction is more negative, did we say that that means it's better oxidized or better reduced? So if something is more negative, or the potential is more negative, that means it's more likely to be oxidized. But we said that as written, magnesium is being reduced. Okay, so that conflicts with what we know from the potential values. So is this a spontaneous process or a non-spontaneous process? So it's non-spontaneous as written. And that's because magnesium prefers oxidation. But additionally, you could also look at iron and say, well, it's less negative, which means that it would prefer to be reduced compared to magnesium. So we really want the opposite process to occur, or rather the opposite process, the reverse process, is the more spontaneous process. Okay, so let's rewrite that in the spontaneous direction. So really what's going to happen is the ion for iron is going to react with pure magnesium to produce pure iron and magnesium ions. So that is our spontaneous process. Okay, so you can also use these cell or these half reaction potentials to determine, is this spontaneous or non-spontaneous? And then you can also figure out the flow of electrons from there. So let's sketch out a electrochemical cell for this reaction. Okay, so we said that iron would prefer to be reduced, not oxidized. Okay, so if iron is actually reduced, is that going to be the cathode or the anode? The cathode. So again, I just kind of remember that because the two consonants are in front. And then magnesium would prefer to be oxidized, and written this way it is. And is the oxidation half reaction the anode or the cathode? It's the anode. So the two vowels go together. Okay, so now for our sketch, remember the anode goes on the left, the cathode goes on the right. So we can just kind of draw an electrode here for iron and an electrode on the right for, already mixing them up. Sorry, magnesium should be on the left. Iron should be on the right. All right, and then we'll connect those with a wire, and electrons are going to flow from magnesium to iron, because remember, magnesium is going to lose electrons, iron is going to gain electrons. And then we also need a salt bridge, so I'll just draw one of those here. And these electrodes are in solution. So on the anode side, we'll have magnesium ions in solution. So maybe we'll use like magnesium nitrate, because the nitrate will just be a spectator ion. And then on the right-hand side, we'll have some iron ions floating around. So maybe we'll use iron nitrate on that side. Okay, so that's our sketch. And now let's go look at the second reaction. Okay, so in the second reaction, iron has an oxidation number of 0 again to start. This time it's reacting with lead ions. So the lead ions will have +2 as its oxidation number. And then in the products, we have iron 2+, and its oxidation number is +2, and pure lead, which has an oxidation number of 0. So iron, we can see, is losing electrons, so it's oxidized. And then lead is gaining electrons, so it's reduced. Now, if we look up the potential values, so I'm just going to write the half reactions over here. So for iron, we already said that the E potential value is negative 0.45 volts. And then for lead, its potential is negative 0.13 volts. All right, so remember, the more negative value is the one that prefers to be oxidized. Oh, went too far. So it looks like iron is more negative in its potential value. So that is the half reaction that would prefer to be oxidized. Looking at what we just discovered, the way that our reaction is written, iron is being oxidized. Okay, so this is spontaneous as written. Let's see, I'm going to make a little room over here. All right, so now let's draw our electrochemical cell. So remember, the anode is on the left and the cathode is on the right. And then we can draw some electrodes. So on the left-hand side, we want the oxidation half reaction because that's what goes with the anode. So we would use iron on the left, and then on the right, we would have lead. And then we'll connect them by a wire, and electrons are going to flow from the oxidation half reaction to the reduction half reaction. Then we also need a salt bridge. And of course, there's some solution on either side. So on the left-hand side, we have some iron ions floating around. And on the right-hand side, we have some lead ions floating around. Okay, so hopefully this isn't too bad. In the next lecture, we're going to just work on some of the worksheet problems. A lot of them are really similar to what we've already done. So if you need some help with those, you can watch the next video, or you can skip the video and just look at the worksheet key. Either one is fine. Although I did not include the answer to problem number 2 on the worksheet key. So if you do want to see the answer, you do kind of have to watch the next video. All right, so I will see you there.